Hello everyone. My name is Seongjae Cho, who is working as an associate professor in the Department of Electrical Engineering at Gachon University. So some of you might remember that this is my second talk, which was the first one was made in last year, August. So I'm very pleased to have another chance to make a talk about memory technologies and future research plans with descendant students at Seoul National University and respective professors. So today I would like to talk about memory, but I would like to go down a little bit, down to the bottom of fabrication. So as can be implied by the title, the most efficiently crafted semiconductor device is memory, and the future computing can be expected therein. So research background, device and fabrication technology with a strong focus on memory. So this is just a reminder, some slides have been brought into this new one from the first one. So I would like to introduce this slide as a reminder. So the semiconductor technology has driven by three horses, which were materials, processing, and device and circuits development. So we can use metaphoric expressions for semiconductor technology driving force as troika, driven by these three different horses, but they are different, but they are running together and intimately related, and they are in the supporting relations. Actually, they cannot be separated. So if you look into the IRDS, the roadmap, the semiconductor technology roadmap was named as ITRS, as you can remember, but its name has been changed to IRDS from since 2017, several years ago. And the materials, I put boxes with different colors for identifying the major concerns that need to be considered in making up the roadmap, future roadmaps. So the first one is material. So starting substrate is always hoped to be a silicon or a silicon insulator, but the bulk silicon is known to be much cheaper than the silicon insulator wafers. And then N channel and P channel can be together, channel devices can be together fabricated on the silicon or SY platform to construct the digital circuits and analog integrated circuits. And logic device structure operations, the novel device structure are always biggest interest in the device engineers. And then FinFET, fully depleted SY and LGAA means non-wire actually naturally put gate around the structured field effect transistor, and it can be evolved into a vertical Y and monolithic three-dimensional integrated circuit that can be scaled later. And actually, the researches are already ongoing in many places. And the last thing, the mechanism transport scheme can be differed, can be changed from the conventional drift diffusion and to post-ballistic and tunneling or junctionless FET and negative capacitance multiple transistors can be skimmed, and also they are already under private researches in many places. So the reason the overall the purpose, the final aim of these various trials are aiming to make the device more light, smaller and energy efficient, so that the our system can be very energy power efficiently operated. So I just like to summarize the memory technologies I have developed so far, experimentally, just by giving some images from the published papers. Flash memory, three-dimensionally structured flash memory, and polysilicon-based capacitorless DRAM, which can be also termed as wanted DRAM, and silicon processing compatible emerging devices, memories, germanium oxide, silicon nitride, and just PRAM ultra-thin floating gate flash memory, and zirconium doped hafnium oxide, RAM, and other memories have been researched. So among these various memory technologies, I have been more intensively involved in two memories. The first one is flash memory, silicon-based flash memory, and the latter is the silicon-compatible registered random access memory. So this shows the three-dimensional folding and flash memory, the process development, the unit process development, and the final fabricated devices in the array and the measurement results. Although the measurement results are not really good actually, so the threshold voltage shift is too much small. So I have much better results, but I just wanted to implement that figure into this size because the 20 nanometer was the thinnest dimension, smallest dimension I have fabricated so far without depending on even lithography. That is fabricated by cycle spacer technique, which is commercially used in the integrated device manufacturers like Samsung or SK Hynix. So that is the record dimension I have made shared so far. So I just brought it here for memory. So the array floor plan and the microscopic view of a single device are demonstrated on the right side. And then rigid-switch random access memory, there are a bunch of many materials that can be adopted to resistive switch random access memory, but silicon compatibility it can be the most important key thing for determining whether a certain memory technology can be successful or not in support of the massive production technologies. So germanium oxide and silicon nitride can be two most interesting switch materials in applicable to RAM technology. The figures show measured current voltage curves from fabricated device and register combined with Seongjae modeling and realistic equivalent circuit to evaluate the reliability of the device itself or the array, operation accuracy in the array. So a certain part of this work was collaborated with SK Hynix several years ago, and the rights for the embedded devices while performing this project were actually endowed to the company. So I can say that the intellectual property was transferred to the company indeed. So what I mean is the future memory is always of interest to a well-known company, even well-known companies. So they are aiming at the storage class memories or future memories next to DRAM or silicon flash memories. So RM is one of the candidates. So I got a BS degree in 2004 from Seongjae University, and the thesis was design of 10 nanometer level MOSFET by device simulation. And I spent a short time as an exchange PhD student with full support by NRF in Korea and GSTEC in Japan, and there at IST located in Tsukuba. And IST has many branches, but I worked in headquarters located in Tsukuba, and there I worked on 32 nanometer and 22 nanometer technology node for terminal. In other words, independent gate FinFET design based on semi-empirical approaches. And then I received a PhD degree in 2010 at Seoul National University. So the thesis was about the floating NAND type charge flash memory with the bandwidth engineering storage node and array. So I can say that most of the knowledge and process skills and device physics were obtained during my PhD years. So after getting the PhD degree, I spent half a year at Seoul National University more as a postdoc researcher, and I continued the threat management flash memory in personal development and other novel devices, which are capable of low power operations. And then I spent 3 years at Stanford University as a postdoc researcher, and there I a little bit changed to photonic devices and integral circuits, but still they are in the group of in the boundary of extended silicon materials. In other words, group-driven devices and integral circuits were developed there for future advanced various components. Low power heterojunctions and transistors were developed there. And then I moved to came back to Korea, and I have been working as a faculty member at SNU University and currently an associate professor. So I can say that my research is really dedicated on semiconductor devices and fabricated with a strong focus on memory. So semiconductor devices and fabrication. So this over some following pages or slides, I would like to introduce a brief introduction to the students and other researchers who are interested in device fabrication, the typical ways to design and fabricate the devices. So the first step is gathering material information and selection of base materials on which the devices or circuits you want can be fabricated. So this includes ab initio simulation, atomic level simulation, in other words, and thin film deposition and material characterization can be performed to achieve this goal. So the figures show the atomic level simulation and thin film characterization, including XRD and electron pattern diffraction and AFM, electron force microscopy, that is capable of evaluating the surface and then the morphology that can be investigated by transmission electron microscopy, things like that. So based on this material characterization results and the atomic simulation results, we can obtain the very fundamental material parameters, electrical or optical parameters like effective masses, lattice constant, bandwidth energy, electron affinity, and what else? Density of states in either conduction or valence band, things like that. So as an electrical engineer, there have been little chances to obtain these techniques. So fortunately, learned from these techniques from SNU and Stanford, where I was working as a postdoc from some classes and seminars and things like that. So these kind of preliminary studies strongly supported in higher level device and circuit designs. So after that, so we can move to and then device level simulation, optimal device and process design by technology, computer-aided design, which can be termed in a short word as TCAD. And the material parameters from the thin film characterization or average calculation can be fed into the TCAD works for higher credibility of the simulation results. And critical dimension can be also determined and electrical performances are predicted on this stage. And just as the material parameters can be fed into the device level simulation, the device parameters can be conveyed to the circuit level simulation. So the device parameters obtained from the fabricated or sometimes simulated device are planted into a circuit level simulation. So in a particle case, in particle cases, that unknown devices need to be transferred into a certain circuit. We can use file of A in conjunction with well-known SPICE tools. And then system level simulations and evaluation of the system with regard to target preferences and in particular energy and area efficiencies can be also evaluated. So there are many tools, many good tools which allow us to evaluate the system level performances. Even though we started from material and devices and small area of functional unicircuit, I can say unicircuit. So whether they are really successful or not can be determined in the system level because the final evaluation can be made by the final end users who encounters the system level package or electronic appliances. So we need to have eyes for all these levels together at the same time. So after the preliminary steps are completed, we can go into the stage of scheming the process integration and mask layout. The unit processor developed for the set of optimal process conditions via TCAD simulation and test runs. The mask layout and mask layout can be performed, and we can at the time after all this we can make the purchase order. So I just wanted to lay out some of my experiences to go through all these procedures. So I start with a sketch on paper, blank paper, as you can see on the leftmost side. So I can scan some number structure, the device or array scheme, and the process steps. So the second piece of slide shows a part of integration, process integration. So I myself and my students like to draw the figure three-dimensionally to help look at the critical part of a device or array in various directions, from various directions, and this stage the process simulations can be performed recursively, and then finally we can set up the recipe for our device fabrication, device or array fabrication, and then we can slide that into the fabrication facility. And so most of the fabricated devices were came out from ISRC at Seoul National University, actually in my case. And then the layout, you can see the layouts of 16 by 16 volatile memory array on the rightmost columns. And then fabric for device and array fabrications. So unit processor developed for the set of optimal process conditions and mask layout and the purchaser have been made, and we can get them together, all the simulation results and the device and processing simulation results and the purchased purchase masks, get them together, and walk into the fabrication center to start the fabricating devices array. And then after completing the fabrication, we can bring them out of the fabrication facility and bring them into our laboratory to perform measurement and evaluation. So you can see the figures I obtained them from ISRC, and actually all the figures or images were obtained from ISRC. The furnace and the SEM, scanning electron microscopic image, and inline SEM. The inline SEM is just located just by the stepper, so that the users can identify whether the pattern was successfully defined with the wanted critical dimension or not. And the inspection needs to be carried out every time it needs to be done. And microscopic images, and sometimes we need to have a really close look into the device to have a look at the tiny scale, critical dimension, and the status of interface between two different materials, things like that. So in those cases, we can send the samples out of the fabrication center and spend some time to have a service, off-campus service for transmission electron microscopy analysis. And then after all these procedures, we all our process is performed. So all is performed at 450 Celsius degree, and that is maybe a lowest thermal budget in the silicon processes. Maybe that is the happiest moment, yeah, because all the fabrication, complicated and long time lasting fabrication has been completed, and yes, it is just before we bring the samples to the measurement system. We don't know what really happen. It's just for a joke. And then microscope, through a microscope, we can look into the fabricated devices and tip into the paths where the contact needs to be for electrical characterization. And one last figure shows the PMOSFET IV curve that was fabricated. So this among these seven, this is not an absolute set of right answers, but just based on my knowledge and experiences about semiconductor device fabrication, I can summarize them and lay out the steps for you. So the preliminary steps, the material part, material simulation and material characterization, have been a little bit relatively optional when it comes to silicon processing, because silicon technology is very mature technology, and the materials that are accommodated into the silicon fabrication line are well known in terms of their electrical and optical properties. So we can say that the preliminary steps for material characterization have been a little bit optional in silicon technology, but its importance is getting more and more larger, because if you think about the future integral circuits that can be built up in a three-dimensional manner, the channel material has a low crystallinity. So there might be chances for us to use polysilicon or amorphous silicon as a channel material. So the polysilicon and amorphous silicon have a different, very wide range of material property variation, so depending on the process conditions and critical thicknesses or dimensions and things like that. So the silicon atoms are still there. So we are using the same species of atoms, but the arrangement are become quite different. And even more, we are again more interested in silicon extension materials like silicon carbide, silicon germanium, silicon carbide, germanium, germanium tin, silicon germanium tin, things like that. Because these group 4 materials are very easily combined with silicon by giving one electron and getting one back to itself to make a covalent bond. So compared with other compound materials like 2,6 or 3,5, the group 4 materials are much easier easier to establish a stable covalent bonding with silicon atoms. So in these circumstances, I can say that the importance of preliminary studies about the material or thin film characterization is getting more and more important. So after all these thin film level analysis, device level analysis, we are aiming to design a fabrication, logic and memory devices, and integrated circuits. So the overall story goes like this, and then this holds to not just for memory devices. It can be true to logic and other application devices. So I would like to show the example about what I just told you. There's fabricated device. There are fabricated semiconductor devices fabricated following in this direction. CMOS process integration for 3D floating NAND flash. That was, I remember that is most difficult processing technologies among those I have performed so far. But as I mentioned briefly, most of the advanced physics and process technologies were obtained during that time. So I really thank the experiences, times, and all the respective professors at SNU. And then the German tin was grown by MBE in gas gallium arsenide substrate, and indeed there was in gas buffer which relieves the tension between the germanium tin and gallium arsenide that have a little bit different lattice constants. So if there are a lattice mismatch between the two different materials, the electrical or optical properties are quite differently modulated. So to obtain predicted properties stably, we need to insert buffer layer. That holds to a silicon and germanium together. So germanium has almost the same lattice constant to gallium arsenide. So we need to profile the gradation in germanium fraction to make a good match between germanium and silicon. So that is usually it can be frequently found in the 3.5 semiconductor devices and materials. So the second one shows the optical devices, microdisc resonator with 20 nanometer free spectral range. And that was the first demonstration of germanium photon resonator in the IEEE journal. So the advisor at during my postdoc researcher just told me that the germanium tin have been researched for a long time since middle of 1990s, but someone who fabricated, I was the first person who fabricated something with germanium tin. So that was not offshoot, that was acknowledged by my advisor there, but that was good experience. So, and then LED, germanium light emitting diode operated by form of LED transport that is also 1550 nanometer wavelength is the standard bandwidth channel for long distance optical communication. But in order to achieve that wavelengths, ternary or quinary compound semiconductor materials should be prepared with a very accurate control over individual atomic fractions, so which is very critical and tricky in semiconductor processing. But you can think about, you can imagine how it would be beneficial if that optical communication channel can be obtained provided by a single species material. That is germanium. So, but one drawback is germanium is technically grouped into an indirect boundary material. So there should be prepared for delivering the carriers that can be combined with the weighting holes there. The aluminum gallium arsenide with 30% of aluminum fraction was found to be successfully transfer the electrons from the R gas layer to germanium p-type germanium substrate, and amplically it was the emission of 1550 nanometer wavelength was emitted from the fabricated device. And on-chip integration of gallium arsenide laser for detector and bioapplication biosensor. The device was evaluated as biosensor in collaboration with the medical school of Stanford University and UCLA and University of Toronto. So that was also a very interesting and fruitful time. And photonic devices, germanium silicon can provide us with a high-speed photon detector. And before that, germanium needed to be germanium with a circuit fraction needed to be characterized first prior to device fabrication. So the fabricated devices show the very good quantum efficiency and high-speed operation capability. So the overall device fabrication can be initiated from silicon, but the overall philosophy starting from the sketch and the devices and process simulation and atom level simulation and circuit simulation and system level evaluation, processing, unit process and process integration developments and evaluation are the same and similarly hold to every semiconductor devices, no matter what applications you might have later. So photonic devices, optical devices, and biosensors, and high-speed electron device, and transistors and memory devices. All of these electron devices are under the same procedures to realize them. So, but although the process technology is the way of the journey to realize the technology are the same, seem to be the same. Most efficient process technology can be found in memory devices and array. So I just it's the story to tell the story. It can be very wide and deep. So I just would like to demonstrate two examples of memory devices in array. I just skimmed apart exquisite processing technologies. Of course, I did my best to reduce the number of processes as small as small number as possible, but the most brilliant exquisite processing technologies have higher chances to be found in memory devices and array. So two terminal capacitorless DRAM with silicon germanium heterojunction. So this is called thyristor RAM or TRAM shortly, and this is one example of capacitorless DRAM. So, but actually the operation itself is totally different from the thyristor, original thyristor, which was invented for power devices a long time ago. But due to the fact that the doping profiles, junction profiles are the same with the thyristor, we can just like to call it thyristor RAM. So the first of all, device physics to implement a one-tip memory devices should be closely silicon understood first. Then unknown materials parameters can be obtained from the existing literature if possible, or while performing can be done while performing the unit process developments. Wanted DRAM or capacitor DRAM devices are under very extensive researches these days in Korea and in the United States. This capacitorless DRAM thyristor RAM TRAM might have 3 terminals or 4 terminals. So the 3 terminals or 4 terminal TRAM were invented long time ago, and actually their prototypes were fabricated and announced by AMD and GlobalFoundries quite a long time ago, about 10 years ago, quite a long time ago. And the final destination of this structure can be 2 terminal devices. So this was actually I and my collaborators published this result. Although it was a simulation result, the idea was quite admitted to be good. So it was published in Electron Device Letters, which is one of the representative device journals several years ago. And I also hold the Korean and US patents for this device, 2 terminal thyristor RAM. So after understanding the device physics and material properties, we can confine the knowledge and data into the device simulation, as I briefly mentioned in the previous slides. And then we are allowed to optimize the device at this moment. So the speed and power consumption and the reliability and sensing margin, things like that, critical dimensions can be adjusted through device simulation. This is not absolutely right, but it can suggest us good guidelines. And the process condition finalization and mask layout can be follow the device simulation. For device fabrication, I wanted to introduce 200% of germanium into silicon to have silicon 0.8, germanium 0.2 alloy. So the final process conditions can be determined by device simulations, but the device simulation results are not always true. So sometimes from time to time, even in the fabrication facility, we need to perform test runs and material characterization. So not just at the beginning of the process, so whole process, we need to sometimes perform those kind of jobs in the middle of process integration or device fabrication at any time we want. So the mask layouts are designed, and the number of masks is the same with the number of photolithographic processes in the fab. Cell process integrations, wafer preparation and cleaning, active formation, and photolithography for B-line, active formation, B-line ash. That can be made down to the bulk silicon down there to isolate the different walls, different B-lines, and photolithography for finish and B-line finish. So the second edge, dry edge, should be stopped somewhere in the middle of the orange colored region, because that is the M plus region that was formed on the p-type silicon substrate. So that is the places where the beeline contacts need to be formed, and then middle temperature oxidation can be performed for gap filling. So the gap filling needs to be performed prior to high-speed, high temperature rate CVD, PCVD, or if when we carry out PCVD or HDPCVD to deposit silicon dioxide in the fast time to isolate the B lines or some metallic connections, there can be some void. So we need to introduce very slowly depositing, oxide depositing technique for the initial gap filling first. And that equipment is also installed in the ISRC. The beeline isolation oxidation and planarization for wall line formation and contact hole edge metal deposition and photolithography for patterning and metal dry edge and oxide thin edge. So, and finally, I would like to skip some figures for saving time. And wall line metal formation and metal lift top cleaning and alloy will lead us to completion of device fabrication. So from time to time, at any time it is necessary, we feel it to be necessary, we should look into the device on the fabrication. It can be microscope simply, or sometimes it can be a scanning electron microscope or transmission electron microscope, and we can identify the material, the interfaces and critical dimensions, and sometimes it can give the correction. It can provide the correction to the previously set up process conditions sometimes. So the fabricated array is shown in lower row. The cell image and microscopic images are demonstrated there. And surely, after walking out of the fabrication facility, we need to measure the device and find out the electrical characteristics from the fabricated devices. And this was actually a volatile devices, volatile memory, and it shows gradual resistance changes, and I was able to have a glance into the applicability as a volatile synaptic memory device. And then the second example is memory logic integrated system, integral circuits. The memory devices and MOSFET devices, CMOS logic devices, and memory devices can be integrated together on the same wafer. So, if possible, this batch process will be more and more beneficial to heighten yield, process yield, and chip yield, things like that, and time saving, good for time saving. So, NMOS transistors and inverters were fabricated on the first floor, first layer, and the memory devices were fabricated on the second layer. Actually, the levels were different in vertically. Instead, the area in which the memory devices were supposed to be fabricated were prepared to be blank. So having the NMOS transistors and inverters around it. So we first went through the CMOS part fabrication first, and then went up to the, in time sense, went up to the memory device fabrication. So we used the 30 masks, and the total steps were 98 in number. So marker, active, poly, source drain junction, dumping substrate contact, and device active layer, and oxide on pattern, things like that. So we have three masks, and we can predict that there should be 13 kinds of photolithography processes. And we need to, as mentioned briefly, we need to take a look into the wafer surfaces or devices, so marker patterning, and deep edge, active definition, and structure, isolation by mass structuring, and MOSFET fabrication, and inverter fabrication can be glanced through the microscope. And the measured electric characteristics can be measured by some set of measurement equipments like Carefully or Agilent series equipments. So the transistor shows acceptably good characteristics, and the invariant. The VTC shows the typical inverting curve from the fabricated inverter. The one difference between the fabricated inverter and conventional CMOS inverter is that those inverters were fabricated only by MOS transistors to reduce the number of taller processes. So it is called active loaded inverter, as you already know from some textbooks from electronic circuits. And the lower image shows the memory device, which has the shear channel below 100 nanometer, and that was constructed not by photolithography technique, but by sidewall patterning technique. So I hope you could have a grasp of how much the techniques and knowledges need to be collectively getting together to fabricate the memory devices, memory array, compared with the optical devices, photonic devices, and logic devices. So the collective knowledge and fabrication skills need to be merged together to implement the memory system. So, but it can be done by yourselves, right? The past, current, and future of the speaker. So I understand that I'm standing here for make a speech about the memory technologies and research directions for the descendant students at SNU, but there can be some professors and I can be an interviewer. So I would like to show some introduction of myself a little further. So I have been focused on memory devices and array technologies and device physics and the realization way. In other words, the fabrication techniques to realize this very complicated, very highly exquisite electronic system by hands. So in the future, not in the future, it is being realized already. So the memory devices are moving into the processor. So it can be a second processor, so helping the central processing unit, or but it can eventually the CPU can be the final destination of memory. So the neuromorphic devices and neural circuits can be one of the final destination of all these technologies. Namely, can be named as processing memory. So the semi-floating gate synaptic transistor and polymerized charge trap synaptic transistors, they have all these core-shell dual gate and sidewall dual gate synaptic transistor. They are a little bit differently named, differently shaped with a different structure and different number of terminals to effectively realize the function for functionality of biological synaptic devices, or sometimes they can be implemented in a neural circuit for high speed or higher energy efficiency. But the basic principles are have been already obtained. It can be found in the device physics and memory operation principles. So this the destination of this my research, past research, are heading for the system level. I believe this is a high time to modify and develop the conventional memory devices more suitable to memory-centric processor technologies. So achievements, the total number of technical papers are 492, and patents are 50 issued in 5 Korean and US patents. So all these achievements are based on the research results on semiconductor device and fabrication technologies with an emphasis on memory. Just for interesting story, I usually give these badges to the class students. So after the students complete the classes successfully, some memorial badges are given to them. So the left one is, as you can see there, it says very, very important information on silicon itself. So lattice is the structure, lattice constant, and energy band gap, electron affinity, and electrical permittivity, things like that, and the transistor IV equation, things like that. And so if one completed the semiconductor class, device class successfully, I give them these badges, and then in the later years, the students have chances to take courses about silicon-based VLSI systems. So after that class, I used to give these badges to the students. So that's pretty. So the education philosophy is concept by words in short. So construction of concrete knowledge to which one can explain the definition of something only verbally is aimed, is required for everyone. So you can just think about the street talking. If you encounter someone who doesn't know what you know, you need to be able to teach them, explain them without paper, pencil, and things like that. You cannot draw and cannot answer. That definition is just something over something multiplied by something. This cannot be understood by the streetwalkers, right? So this long time trains, long time exercises to picture drawing and calculation by hand will provide you the concrete knowledge of something eventually. So I convey this mind to everyone I met, and education. So it's not even in the class on Gachon University. When I step out of the campus, I can see many people who wants to learn semiconductor devices and fabrication. So in a University Semiconductor Research Center at Seoul National University, I take in KAIST and the inspector's education at Korean Intellectual Property Office, and sometimes I was invited to companies. So every time I meet them, as I start with this mind. So selected awards and prizes, I was awarded by IAIA maybe 11 years ago. They awarded the Heterojunction Engineer Award. One award was selected who is under age of 40 and awarded once a year. Recently, I received the Minister Award from the Korean Ministry of Science and ICT for developing the ICT fundamental technologies. So there was one award in the semiconductor module. So research projects. So I have gone through. I have performed successfully completed 12 projects so far, and ongoing projects I have 4. There's 4, and 2 are upcoming. So 12, I was in charge of, principally in charge of 12 projects out of this total 18 projects. So maybe it is the last moment I should put my talk today. So I wanted to convey the knowledge and experience of semiconductors. Semiconductors can be divided not strictly, but very roughly. It can be divided into devices of fabrication and circuits and into systems higher level. And devices can be further divided into CMOS logic devices and memory devices. And in terms of material, we are still and always will be interested in silicon and extended silicon, which is group 4 materials. And this material-oriented fabrication will be of our everlasting interest, right? And circuits and research systems, the hot topics are artificial intelligence and processing memory. But I believe this is a very high time to for the circuit and integral systems and devices fabrication part may encounter very closely over the bridge of memory technology. These two technology areas can be linked very intimately, linked together through memory technologies, I believe. So the future technology can be. This is actually my future plan. Due to a lot of times, a substantial level of time, I just wanted to summarize my future plan with this single slide. I will develop memory devices and fabrication techniques on and on, but the final destination of memory technologies can be memory-centric future computing systems. So memory and processor cannot tell you are you, I am I. So sometime in a very near future, there should be some moment that memory is processor and process itself is memory, and that is just around the corner, I believe. Okay. Thank you very much for your attention today. Thank you.
네, 조성재 교수님, 좋은 발표 해주셔서 감사드리고요. 시간 관계상 혹시 질문 있으시면 한 분만 받고 가도록 하겠습니다.